Okay, it started. And thank you a lot for accepting presenting today, Jasper.
Yeah, thank you for having me. Thanks for the kind introduction. I'm Jasper, and I'm from the University of Hamburg. I'm a student and researcher, and also a member of the Hamburg Bitbots, which is, as Grégoire already mentioned, a team that participates in the RoboCup. I'll talk a bit about that in a moment. And yeah, today I'm going to talk a bit about our Wolfgang-OP platform, which is a robot platform, which we developed in the previous years based on research from other teams or from other research institutes. And yeah, I'm going to talk a bit about what kind of aspects we focused on and what kind of improvements we made. So before we start, I would just like to show a picture, because I know how annoying it can be if you see the title and you want to know what this robot actually looks like. So this is the robot in the real world. It's about 80 centimeters tall. And we also have a model for it in the PyBullet simulation and also in the WeBot simulator. In the WeBot simulator, as we already talked about a second ago, if you were there, is currently used in the RoboCup as an alternative to a real competition because of obvious reasons we can't meet. So I structured this presentation a bit like a paper, because it's based on this paper, and I can send it around after the presentation as well. And yeah, I'm going to talk a bit about what motivated us to build a new robot platform, or to work on this robot platform. I'm going to show a bit of other robots which this work is based on. And I'm going to show you basically all of the aspects which we focused on during the development of this platform and how we evaluated them. And of course, a short conclusion of what we achieved. So yeah, we want to have a robust robot, because there's obviously, we want to have less maintenance being done on this robot. This is annoying, this takes time, it costs money to replace parts. So we want to make sure that it doesn't break. And we also want to use it for these RoboCup competitions. And they have to be robust, they have to work without breaking, or as long as possible without breaking for a while. As a second point, we want to have it be low cost, also for obvious reasons, because spending less money is sometimes also good, but also because we want to have multiple robots. So it's a multi-agent system, which is also interesting for research purposes. And also this kind of lowers the barrier to entry. This makes it easier for more research groups to enter into the field of humanoid robot research, if they don't have to spend like 500,000 euros on a very expensive robot. We want to have a high computational onboard power, because in recent years, basically in the last 15 years, the processing capabilities went up, and also the processing requirements went up. For example, for neural networks, it takes a lot of computation there if you want to process some images. So this is kind of a point which is bad in some robots, so we wanted to improve on this. And we also want this to be a bit larger, because basically we want to move towards having a full-sized humanoid robot. So for example, the Darwin platform, which I'll show you in a moment, it's like 40 centimeters tall, and it's much different to have that small of a robot than to have a larger robot. So basically moving towards having a full-sized human robot which can assist humans in their tasks. And also we want to focus a bit on actuator power, because this allows us to do more dynamical movements, to walk faster, to in this context kick the ball a bit faster, but also to manipulate objects which are heavier. So this is all placed in the RoboCup Humanoid League context. It's a soccer as a research competition, basically. There's two size classes. We play in the kid size, the smaller size, which is 40 to 100 centimeters. So we are with about 82, 84 centimeters. We are quite tall robots for this size class. And one of the interesting aspects is that the robots, they have to have human-like sensors, which means they are not allowed to use depth cameras or LiDARs, for example, but just a normal camera, an RGB camera, or multiple RGB cameras for stereo vision. And the body proportions, they have to be humanoid. So they cannot just have enormously long arms or enormously long legs and a very small torso. So this is meant to such that the robots still look a bit like humans, because we want to have them in the future at some point back in our human world. Yeah, and they're basically games being played, 2 10-minute halves, making a 20-minute total. And in the small size, in the kid size league, there's 44 games, so it's quite a lot of robots interacting with each other, and 2 against 2 in the adult size. So I brought a small video just to show, if anybody of you does not know the RoboCup context, how it looks like basically. So this is from the final from 2019, the last real competition we had. These are the robots from Team Roban. Grégoire is with this, or was, I'm not sure if he's still with this team. I believe he's still with this team. Against a team from China, the ZJU Dancers. So you can see these relatively small robots manipulating a relatively small ball on a field which is, I believe, 6 by 9 meters are the outer lines. And yeah, they're trying to manipulate this ball into the goal as in real soccer. So this is basically just an application which we use to develop software for humanoid robots. It's a bit like the Formula One, where you develop new components for cars. We use this as a as a research platform to further the development on humanoid robots. Yeah, so here we can see there's multiple tasks involved. So they have to do omnidirectional walking. They have to walk into all directions and turn around. They have to stand up themselves when they fall down, and they have to manipulate the ball, for example, with a kicking motion or by dribbling it. Yeah, thanks to Silvia Schmidt for this video. She did a film on RoboCup 2019, and if you want to have more information about it's a full movie actually, or it's pretty long. If you are interested in this, if you want to have some nice movie to watch about robot soccer for the evening, then you can check her out on the website. Yes, I believe I have some. Yeah, so next up we're going to talk a bit about the related work. So what other people have done. So one of the original robots of this size class, or one of the most famous robots of this size class, is the Darwin open platform. It's 44 centimeters or 45 centimeters high. It has 20 degrees of freedom, meaning 20 joints which actuate. And one of the main drawbacks is it has just a very basic single core processor, which is also due to its age. It has a pretty bad camera, so there's a lot of motion blur in this camera, which is kind of very difficult if the robot is moving rather fastly. So they made a small update, which is the Robotis-OP2. So Robotis bought this whole platform, and they now sell it as the Robotis-OP, but it's basically still the Darwin. And here they just upgraded the processing capabilities slightly, while keeping the same mechanical design. In the third iteration of the platform, they also upgraded the processing capabilities quite a bit. And they put on a better camera, which is basically just a Logitech webcam, which still has a lot of issues with the motion blur, because it's still not really a good camera, but rather a camera meant for like web meetings on Skype calls and so on. And they redesigned the mechanical part of this whole robot. So it's slightly taller, with now 51 centimeters, and it's also slightly heavier. And what they also changed is the subcontroller board. So basically the board which interfaces between the motors and the computer, and does some, basically the protocol translation, and also has some sensors on it, like an inertial measurement unit. And they improved that as well. This was also really a big issue in the previous platforms, because there were major functional issues with that. So now let's move to the Nimbro open platform, which was developed by a research group in Bonn, called Nimbro. It's also a team that participates in RoboCup, and this robot was also built for RoboCup. And basically this is what our robot is based on, 2 generations afterwards. But they changed also basically the height quite a lot. They increased it to 95 centimeters. They changed the materials used. So they used composite carbon. So basically the carbon fiber or whatever it's usually called, or carbon fiber reinforced polymer, I think is the official name for it. They use different motors, which are a lot stronger, which is also required due to the larger size and therefore the higher mass. This is still also 20 degrees of freedom. And it has basically the subcontroller board from the Darwin, which was a major drawback for this platform because it's there's major issues with this board. They also introduced some 3D printed parts, for example, the head or the spacer between the hands. But these are just minor parts which have been changed, so they're not structural, or the structural parts are still aluminum or composite carbon. And the camera they use is very similar to the one that the Robotis-OP2 uses. So next up, I'm going to show you a bit of Hambot, which is a robot which was developed at our lab in leading up to 2015. And the main point of this robot is that it's fully 3D printed, except for the electronics and motors, of course, because those are really hard to 3D print. But the idea is basically replace all the metal parts with plastic parts. And this was a very interesting piece of research back then, because 3D printing was relatively new, and a really easy way of manufacturing parts compared to having to have a CNC machine, and also quite a bit cheaper because the manufacturing is just decreased, or the manufacturing cost is decreased quite a lot. This robot also has 24 degrees of freedom compared to the 20 degrees of freedom that the previous robots I showed you have. So this included a hip joint, which can basically tilt the hip and also move the pelvis forward and back and to the side, or the torso can go left and right and to the front and back. And there's also a toe joint. So the toe can be used during the walking. This platform, however, was really highly experimental, and there were also some major issues with it. So we did not continue this further. What we believe this was quite an interesting piece of research in terms of what can be done with 3D printing in humanoid robots. And we also applied a lot of the concepts we explored there in our current robot platform. As an intermediate, basically, between the Nimbro open platform and our open platform is the robot from the WF Wolves, which is a team also based in Germany. And they kind of changed the carbon parts a bit, such that the robot is slightly shorter. And what they also introduced was these compliant elements in the shoulders. You can see them here in pink, orange-ish. And they lead to when the robot falls to the side, there's quite a big impact on the elbow, and basically a lot of torque being applied to the motor's gearbox, and this breaks the gearbox frequently. And this compliant element allows for this gear not to break. They also upgraded the electronics a bit, so they used a new controller board. And they also, it's not really visible in this version of the robot, but in another version of the robot, they introduced an NVIDIA TX2, NVIDIA Jetson TX2, which is basically a small graphics card meant for running neural networks on mobile platforms. So there's a lot of other robots out there, which I haven't talked about now due to time constraints. So there's the Sigma Bun from Team Roban, the iCub from a laboratory in Italy, which is also about 1 meter tall, I believe, and very expensive. There's an adult-sized robot, Nimbro OP2X, and other adult-sized robots like the Tormeng, the Telos, the Atlas, the Asimo, or the THR3, the Toyota research platform. if you want to know more about different robot platforms, I invite you to look into the paper. We've written a bit more about other robot platforms which influenced us here, and yeah, how we came to this decision of, or the decisions we made while building this robot. So now to our robot, we basically have 4 main improvements that we made to this, to the robot from the WF Wolves, which is based on the Humanoid-OP. And what we added was 3D printed elastic elements. So previously in the Wolves robot, they were not 3D printed. We added a parallel elastic actuator. I'm going to show you a bit further what that actually means. We made quite some upgrades on the electronics and sensing capabilities of the robot. And we increased the computational performance by introducing some new computers and other things. I get to that in a moment. So let's talk a bit about these elastic elements. Basically, these are just 2 pieces of plastic which are screwed on top of each other, and then they are in series with the motor. So in the kinematic chain, you have this one link, then you have the elastic actuator, then you have the motor, and the motor is connected to the other link of the robot. So what these do is they basically are for absorbing a shock, but what they introduce on the other hand is some uncertainty in the movement of the position of the arm, for example, in our case, of the joint in general. Yeah, so on the right you can see what it looks like. It's relatively small. So I believe the diameter is about 8 centimeters. I would have to look that up exactly, but yeah, and this is made from a NinjaFlex TPU, which is a thermoplastic polyurethane, I think the name is. And this is a material which can be 3D printed relatively easily, and produces very elastic part, or these parts are relatively elastic and very resistant. So we didn't have much problems with these breaking at all. And we also introduced one in the neck joint of the robot. If I go back to the picture of our robot here, you can see it on the left side of the neck. There's also a compliant element. We had some issues previously with the robot falling to the front and then the neck joint breaking due to the camera weight, but this is basically gone now. So let's get back to the elastic elements. As I said, these are based on the work from the WF Wolves. They made them out of a different material, which was not 3D printed, but rather milled from basically a piece of stock. And this was really, in our opinion, a very difficult manufacturing process, because this milling process is kind of hard to set up, and just 3D printing it is relatively cheap. So we also introduced some elastic elements in the front and the back of the robot. Can you actually see my mouse?
Yes, Jasper, we can.
Okay, so you can see them here in the front and the back. They're basically triangles. These are also from the NinjaFlex TPU. And when the robot falls to the front or the back, these greatly introduce the shock that's transferred to the torso of the robots. And because there's a lot of mechanical parts inside, or mechanical fasteners, it's better to have a less strong shock, so these don't break or these don't wear out over time. So how did we evaluate this robustness? We also developed a fall classifier, which goes into a safe position when the robot detects the fall. And basically this is done relatively quickly. So it takes just 0.6 seconds from this fall basically starting. It's kind of hard to say when a fall is starting, but we try to do this year, or try to put some label on some recorded data we have when the robot is basically in a position where it's not possible to stop this fall anymore by doing some steps, for example. And then the robot moves into a safe position. And it's really difficult to evaluate physical components like this because you really risk breaking the hardware of the robot if you don't use them. So we can say that we experienced less issues, but we don't really have numbers on this because we didn't record previously how often the robot broke. So we don't have a lot of data on this, but we can say like qualitatively it's better, but it's really hard to put into numbers. So yeah, and for the series elastic actuators, this is the name of these round parts in the shoulder. And for the bumpers, we didn't really have any wear after we used them for a lot of hours. So they seem not to have issues with that. We had one element break after basically 2 years of use. And this was really easy and cheap to replace. I mean, the material cost for this is, I believe, in the 2 or 3 euros range. So this is not really a problem. And you can, as they are easy to manufacture, you can just manufacture a few more and replace them in a time span of 5 to 10 minutes. Yeah, so let's get to the parallel elastic actuators. What this basically means is that in the kinematic chain, parallel to the actuator, parallel to the motor, there's another actuator, an elastic actuator. In this case, a torsion spring. So basically a spring which you compress by turning it. So it stores some energy there. Yeah, and we put this into the knee of the robot because this is a very heavily used joint in a humanoid robot and also in humans as well. And what was our motivation for this? We wanted to reduce the maximum torque that the robot has to perform, or that the knee has to apply. And why would you want to reduce the maximum torque? Firstly, because this requires less energy. Having a larger torque requires more energy, and due to the loss with the resistance of the motor's coils, having a lower torque in general is desirable. It also produces less heat, and this heat is easily dissipated, or is more easily dissipated, and yeah, basically reduces also the wear on these mechanical components. So to sum this up, basically standing up or standing in general, standing up and kicking becomes easier. So these motions are less of a problem. But in return, because you need to wind up the spring, anytime the robot has to pull its legs towards the body, it becomes harder. So for example, if the robot is laying down, it has to pull its legs to itself to stand up. We see that in a second here. We can just go to it. So basically in this moment where the robot starts off with pulling the legs to itself, this becomes harder. Here in the bottom, you can see the torque graph. But the standing up motion, basically getting from a sitting position into a standing position, this becomes much easier for the robot. So it doesn't have to apply that much torque in the knees. And you can see basically the graph is just shifted a bit, which is also what we expected, but this means that we don't have these high torques in the 6 Newton-meter range here. A word about how we measured this. We didn't put a force torque sensor in there, but we used the internal measuring of the actuators, which is prone to a lot of errors. So these numbers are really hard to be taken as an absolute, but as a relative measurement, these perform fine. Another evaluation we did was during the walking. So you can here see the torque required during a walking phase. In the beginning, the robot is standing on the very left, the robot is standing on its 2 feet. In the middle, the robot is standing on its 2 feet again. So basically, this is a double step. And the first step is the support phase. So where this is for one knee only. So the knee is basically carrying the whole weight of the robot. And you can see here, this is reduced. In turn, when the leg has to perform the step, pulling the leg towards the body becomes harder and requires more torque. Now I'm going to talk a bit about what kind of changes we made to the electronics compared to previous robots. So we made a new subcontroller board, which improved a lot and which is based on the previous research we did. We introduced some foot pressure sensors, which are also based on the Sigma bound robot, which I unfortunately didn't show. We introduced an IMU module, which allows us to place the IMU anywhere. We made upgrades to the camera, and we also introduced some tensor processing unit, which basically is the computation part. So we, in 2018 and 19, we kind of tried to evaluate what's the effect of using high frequency communication with these motors. What does this allow us to do? And our main finding, summed up in one sentence, is that a higher update rate is better. And basically because every time you talk to a device on a bus, it has some delay in the return of its response. And this delay is it's hard to get rid of. So what you do is you split it up into multiple buses. And this is really good to do in the humanoid robot. You're going to probably have all this processing either in the head or in the body. So yeah, from the body out, you can just make multiple buses, one for each leg, one for each arm, for example. And this allows you to basically wait for the responses of multiple devices at the same time. We introduced a lot of quality of life features, which are just nice to work with, but in terms of research, not that interesting. This is what it looks like at the end. The top right part is the splitting it up into 4 buses, and then there's just some basic sensing and regulation capabilities of this board. So it has quite a few features which are more explained more in more detail in the paper. One of the really nice features we introduced was putting in some power over Ethernet injector, which allowed us to just run one cable to our camera, which is quite a nice thing to have, because less cables means less cables that can break. And this also increases the robustness overall. We also introduced a foot pressure sensor, which is based upon a design from Team Roban. It features a much higher update rate. This picture is unfortunately of an old mechanical design, which is still made out of metal, but now our foot is 3D printed. But I just didn't have a better picture of the foot for now, sorry. So this basically allows us to know when the robot is making contact with the ground, and also while the robot is having contact with the ground, where its center of pressure is. So is it leaning to the right or to the left? And this can be very valuable information. For example, when you want to kick a ball, or when you want to walk, you want to know at which point in time is my foot hitting the ground. We introduced also an IMU module, which is basically just an IMU, which is on the same bus as the motors. And this is again a point of robustness. You want to reduce the number of cables in a humanoid robot, because these are failure points. And you also want to have an IMU in the head of the robot, because this way you can do some geometric transformations much more easily, because you have a better measurement of the head's angle compared to the ground plane. And this is also how it's done in humans. I mean, our sense of orientation in the world is in our ear. So inspired by this, we also wanted to put the IMU into the head, and therefore developed this. So we also upgraded the camera from previous models, or from previous related work, quite a bit. We had always this issue of having a lot of motion blur, so we upgraded to an industrial grade camera, which has global shutter, which is also really nice, because it means the whole image is captured at once and not just line by line, which introduces some weird artifacts. It's connected via Ethernet, as I said already. The power over Ethernet is powering it, which reduces the cable number by another one again. And this has a really large sensor, which means you can have a lot higher shutter speed, basically meaning the images are taking more quickly, which then is visible in a lot less motion blur in the image. And this is really nice if you want to detect some features in these images, because they are not just some kind of blurred mess. Lastly, we introduced, or we didn't introduce this, is basically an Intel neural compute stick, which we put into our robot, and we evaluated how much does it affect our performance, how much does it improve our performance. And whereas previously our neural network was running at 11.2 frames per second, we could increase this using this relatively cheap and simple device by about 40% to like 15.5 frames per second. This is really interesting because it's, I think, the first work, to the best of our knowledge, which evaluated how much this performance increase actually matters, or how much the performance actually increased by using this device. Of course, it really depends also on the network architecture you're using. But we had this for a real application, so we believe that this is representative. Yeah, so next up I'm going to basically just conclude a bit about what I just told you. So we built this robot. The price is about 11,000 euros. It's always really hard to pinpoint the exact price of this device because it's a lot of components and they are developed over multiple years. But we kind of summed it up. This doesn't include manufacturing, so there are some aluminum parts in this robot which need to be CNC milled. And this is, of course, if you have to have somebody do this, you have to pay this extra, and this might cost another few thousand euros on top. We made some significant improvements compared to previous platforms in multiple fields, and we integrated this previous work we did to evaluate the communication with these devices on the bus. We integrated this into our robot now. And yeah, unfortunately, the evaluation during a real RoboCup competition is a bit delayed for obvious reasons. So yeah, we wait on this, and we hope to use this in this year's competition and see how well it performs. And yeah. All right, these are some of the references I used in this work, or in this presentation. There's a lot more in the real paper, but I just these are just the ones that we used here. All right, so now if you have any questions, you're very welcome to make them now.
Thank you very much, Jasper. So if you have questions, do not hesitate to open your mic, raise your hand. I think I do have some question to ask. Okay, so currently, I think one of the critical points, I mean, okay, maybe I will turn on my camera again. So yes. Maybe one of the critical points, at least for us, when improving those robots, is limiting the things that break, actually. And today, what are the things that are get the more broken with your robots, the more often? Like, is it the gearboxes, or are there some other parts?
That's a good question, Mark. Do you know what currently breaks the most?
Yes,
I would say it's the cables. So the cables still get in between, like the arms and the torso and so on, and then the isolation gets rubbed off, and that's I guess definitely the worst thing. And it's really difficult to do for humanoid robots, this cabling. With the 3D printed robot, Jasper also showed this Humanoid. We had the option to run the cables quite well through the parts, but it's more difficult with this one here.
Yes, okay, true. I think it's the same for us. Like, cables is a nightmare, and it always break and get stuck. And okay, maybe about dynamic cell connectors as well could be better, but there's something very hard to improve because it will require a lot of electronics rework.
So what we also did it's always really hard to show if you don't have a picture from very close up. But we for the dynamical connectors, yeah, okay, it's kind of hard to see. But we use zip ties to basically alleviate any strain from the connector. So there's never anything pulling on the connector itself. So it's this helped quite a lot with like loose cables or loose connectors, but still cables in between moving parts still get damaged.
Yes, okay. But are you still daisy chaining them, or are you using some kind of you know, a bus with a...
Yeah, so
yes.
It's still daisy chained, yeah.
Okay, yes, okay. Because we experimented both, and daisy chain versus, I don't know how to call it, like some kind of a bus where you distribute, you know, to avoid just going through all the connectors. That's actually... Okay, and another question, you used 3D printing at some points, and now what are the parts made of, and do you have like bad feedbacks about 3D printing for such robots? Like, is it not robust enough, or what is your feedback about this 3D printed experience? I think it was...
So we have the feet are 3D printed, and these are working perfectly fine. There's some connectors in the knee which are 3D printed. They are also not a problem at all. We have the parts between the hands are not really important. They don't break.
So they are all PLA.
Yes.
Okay, classical PLA.
We have the head, which is also 3D printed. I believe that we should switch the head from PLA to a different material. This way we could take out the series elastic actuator in the head, or series elastic element in the head. And because this broke a bit, and now it doesn't break, but you have some uncertainty due to this elastic element in the head.
Okay, but what I meant is as well, compared with you know, the former robots, I think it was Hambot maybe.
Yeah.
You introduced, you said it was all 3D printed, even the joints themselves were 3D printed. But did you experience a lot of breaking on such parts, or?
The main problem with the Humboldt was that we used this MX series from the Dynamixel, and the connection, they have like, I don't know how to explain it, but they have this kind of ring of mounting holes around the servo motor. And if you connect it with a part, there is just like 1 or 2 millimeter of material at some point. And this was always kind of the main issue where a lot of parts broke, because you had like 1 or 2 millimeters of 3D printed plastic, and that does not work at all. The newer X series from the servos has a different mounting scheme, so to say, and it works vastly better to connect the 3D printed part to the servos. So this is much better, I guess. The main issue in Hamburg was that it was too heavy, because it looked nice and it was nice for the cable routing and so on, but in the end it was very heavy, especially the torso. It's like a huge box, as you can see. And here our new robot with the carbon fiber parts, for example, is of course much less weight, and this is of course also important in a humanoid robot. But generally, I would say that it's definitely possible to print a lot of parts even with standard PLA. Often you have to redo the part a second time or even a third time, because the first version almost mostly breaks because you forget like one point. But yeah, it's rapid prototyping, so that doesn't matter so much. And the elastic parts made of TPU, they are extremely resistant and basically never break. Yeah.
Okay. Okay, since that's fine, those very small parts that you can print in batch and keep as like some kind of mechanical fuses, this looks promising to avoid changing gearboxes and.
It's not really a fuse. So it's because it's a fuse. It's just breaking, but this is not breaking if the impact is too heavy. So
Yes, I understand. What I mean is that, okay, at some extent, it's like not a fuse, but if you go further, it becomes a fuse in the sense that that's the thing you are going to change. And I guess instead of changing a gearbox, it's better to change the small CPU parts that's not very expensive.
Yeah, actually, we had this issue with an earlier version of the head where this neck part always broke, the 3D printed one, and then we replaced it with a metal part, but then the servo motor broke. So it was actually better to have the 3D printed part breaking there, because that was really then some kind of fuse, so to say.
Okay, I see. Okay, but now about metal parts, do you still mill as well, or do you mill yourself, or is it standard parts?
No, these are milled, custom milled parts. Actually, they are this for the metal parts, for the aluminum parts. There's also 2 steel parts for the shoulders. The torso is the same as the one from the Nimbro robot, and this is made from an aluminum tube, and yeah, made from this aluminum tube. So yeah, this is kind of a difficult manufacturing step. We were looking into how this could be replaced, but since we already had enough parts for the robots we wanted to build, we didn't make any improvements in this point and focused on other things. So it's definitely, there's still some aluminum milled parts in there, and they are really good in terms of strength, but they might be a bit too heavy, to be honest.
Okay, and do you deal with some bendings, for instance?
So we had some issues in the shoulder, where, yeah, basically if the robot falls to the front without doing a motion to prevent a falls on the shoulder joint, these shoulder parts can bend a little bit, but other than that, and they are like, you can bend them back into shape if you use some pliers. Other than that, we didn't have any deformation.
Okay. Okay.
But they are pretty thick aluminum parts.
And okay, I see. And do you another question about the TPU, the tensor processing units you tried? Did you give a try to, for instance, Google Coral as well, just by chance? Maybe someone in the team. I also heard about it, and
I think at the point that we evaluated this was the only thing that was available.
okay.
So we kind of started this in mid 2019, I think. And this was the only real option for us. So there were not any other products available, so we didn't evaluate others.
Okay, I see. Because this is something in our to-do list, like to compare some co-processors or something we can delegate neural networks. And, Google Coral as well is on the list. That's things I'm interested in some feedbacks if you know.
Yeah, I definitely believe there's better products out there now. So basically the point to put this in here is there is some product like this out there. Use it because it's small and very capable for a mobile platform.
Okay. What I don't understand about the sticks is like how much you can delegate, knowing the low consumption of such devices. Like I think it's a few watts you can pass through USB. So like how much you can delegate neural networks computation using a few watts. That's okay.
So the figure, we don't really know how much power it draws. We haven't checked it. But the figure you see here is basically because you still have to do some processing on the CPU. You have to grab the camera image, pre-process it a bit, and throw it into this over a USB connection and retrieve the results. So these 11.2 FPS is basically having a single core of the CPU just performing the neural network, and this 15.57 is basically a single core of the CPU using this and the TPU, the NCS, the neural compute stick.
Okay. Okay, I see. But that's definitely an interesting way to go, because even if we use GPU, it will be for neural networks. So anyway, I think we'd better investigate on such devices and use such devices. It might become very common. Okay.
I mean, it kind of started off with the Jetson TX2.
Mm-hmm.
But the Jetson TX2 is heavy, and it's basically a whole new computer in there.
True.
And yeah, this is kind of an improvement on that, because I mean, if you wanted to use the Jetson, you wanted to use it for doing neural networks.
Yes, true. But I think it will be this. I'm not sure again, but I think it will be similar with the Google Coral. I think it's like another computer, and you need to get some protocol or something like that to communicate. But I'm not sure. Again, I'm talking, and if people are experienced, I'm interested in feedbacks. Okay.
The plus side on this sticks is also that it's easier than having a second computer in your robot, because
yes,
you don't need this communication, and it's like really just a library call, so to say, to execute it on the stick. So it's really easy to use.
Yes, I see. That's such an interesting lead, actually. And about the new design of the PCB for the fit, is it this is open source on your repository as well? Or?
Yes.
Because it's likely we have maybe a master students working on that, among other things, because it's true that our original design is very cheap Chinese amplifier, and with a very slow and inaccurate sampling range. So of course it's sufficient to know if you are just on the floor or which foot is supporting the robot. But of course we can. I think it's interesting. So maybe I will investigate as well. Okay.
Yeah, I can send the paper into the Zoom chat, and
yes.
there's all the links are in there.
I think I will send it by email to the people from the mailing list, and as well with the video, I will put a link, maybe if you want, on your GitHub or website or whatever is the best, or the paper itself on the for the archives on R4 websites.